Hello, so in this video I'm going to go over about 14 problems from chapter 14 on kinetics. So I'm not going to go over this too much because I think you've seen these before, so I'm just going to get right into it. So it says, given the following balanced equation, determine the rate of the reaction with respect to hydrogen. So before we actually do this, what I would like to look at is if we have A's yields B's. Well, what is the rate? The rate is equal to negative 1 over A delta concentration A over delta T. So this is the rate at which concentration will change. Note that it's negative because it's a reactant. So reactants are going to get consumed during the reaction. And this is equal to positive. You don't necessarily need to write positive, but to emphasize it, I'm going to write positive. 1 over B delta concentration B over delta T. And why is it positive with respect to B? Well, it's positive with respect to B because B is a product which is going to get formed during the reaction. And we need to use the stoichiometric coefficients because it depends on how many of the A's or how many are reacting or how many of the B's are forming. So we do 1 over the stoichiometric coefficient. So let's look here for hydrogen. Hydrogen is a reactant, so it's going to be negative. The stoichiometric coefficient is 3. So negative 1 over 3 delta concentration H2 over delta T. This, choice letter D, expresses the rate of loss of, in this case, hydrogen. Question 2 says, give the characteristic of a second order reaction having only one reactant. Well, let's write the rate law for a second order reaction with only one reactant. In this case, my reactant I'm going to write as X. So rate equals K, concentration of X, but because it's second order, it's squared. So it's the concentration of X squared, because it's a second order reaction with respect to X, the only reactant. It says the rate of the reaction is proportional to the natural logarithm of the concentration of the reactant. No, that is not true. In the integrated rate law, the natural logarithm plays a role, but here the rate, there's no logarithm, so that's not correct. The rate of the reaction is not proportional to the concentration of the reactant. Well, that's not true. Okay, the reactant is in the rate law, so therefore this is not the answer. That would be if it was a zero order reaction, then it wouldn't matter what the concentration of the reactant was. The rate of the reaction is directly proportional to the concentration of the reactant. That would be for a first order reaction, but that's not the case. The rate of the reaction is proportional to the square of the concentration of the reactant. Yes, the concentration of the reactant is squared. So choice letter D is our answer. And the rate of the reaction is proportional to the square root of the concentration. That would mean this was 1/2, which is clearly not the case. So the answer here is the rate of the reaction is proportional to the square of the concentration of the reactant. Question 3 says, what is the overall order of the reaction given the rate law? And we're given rate equals K, concentration X, concentration Y. Said another way, the reaction is first order with respect to X and first order with respect to Y. So it's first order plus first order, which means the overall reaction order is second order. More generally, if you want to know the overall reaction of the overall order of a reaction, simply sum the reaction order with respect to the individual reactants. So notice that we use the rate law, not the stoichiometric coefficient. There are two y's here, but this rate law says that this is proportional to first order, with respect to y. So first order with respect to x, first order with respect to y, 1 plus 1 is 2, second order overall. So question 4 says, it says determine the rate law and the value of K for the following reaction using the data provided. And this is a very long question, so we're going to have to do a lot of work in order to figure this out. So the first thing I want to do is we have 3 different trials, and I want to label these 1, 2, and 3 so it's clear where I'm getting the data from. Now I need to find the reaction order with respect to NO2 and with respect to O3 in order to determine the rate law. Note that I can't simply use the stoichiometric coefficients. That's going to be a problem. So the first thing I want to realize is I want to write the general form of the rate law. So the rate is going to equal to K, concentration of NO2 to some N, I guess M, and concentration of O3 to some N. So I don't know the order of M or the order of N. So what I want to do is I want to use this information in trials 1, 2, and 3 in order to figure that out. So what I'm looking for, I'm going to do M first for NO2. I'm looking for something where the concentration of NO2 changes, but the concentration of O3 is constant. So in the first case, if I look at the first one and the second one, the concentration of NO2 is going to be constant, so that's not going to work. But if I look at 2 versus 3, the concentration of NO2 changes. What about the concentration of O3? Well, the concentration of O3 remains constant. So I want to, for NO2, the rate order with respect to NO2, which is going to be M, I want to compare reactions 2 and 3. Now I want to write the rate laws using the information provided for both of them. So the rate is given. So I'm going to do 2 first. So here's 2. The rate, which is given, sorry, I didn't want to write rate, I want to write the rate, 2.84, equals K, the concentration of NO2, which is 0.10, to the M, which I don't know, and the concentration of O3, 0.66, to the N. For reaction 3, I want to do the same thing. So this time it's 7.10 equals K, 0.25 this time to the M, 0.25, and 0.66 to the N. Now, in order to find or simplify the variables, I want to divide all of these. Well, what cancels out? K cancels out. 0.66 to the N cancels out. And what I get is 0.28, oops, not 0.284, 2.84 divided by 7.10 equals 0.10 to the M over 0.25 to the M. To simplify this, I can say that this, which is 0.4 mathematically, equals 0.1 divided by 0.25 all to the M, which happens to be 0.4 to the M. So I just took 0.1 divided by 0.25 and raised it all to the M power, because that's how the math works. So this is the same as these two things, both raised to the M. Well, if 0.4 equals 0.4 to the M equals 1. Now, if you had to actually do this, you could take the log of both sides, take the log of 0.4 equals M log 0.4, and then divide log 0.4 by log 0.4, and you'd find that M equals 1. But because these are the same number, you don't actually need to do that math. All right, so now I know that M is 1. So now I know that it's first order with respect to NO2. Now I need to find O3. So for O3, which is N, the reaction order with respect to O3, I need something where O3 is changing and NO2 is constant. So if I look at 1 and 2, that's going to work. So I want to compare 1 and 2. Why? Because I want O3 to be changing and NO2 to be constant. Now I write the rate laws. I'm going to start with 1. So for 1, it's a rate, which is given 1.42. Whoops. Let me try again. For 1, it's 1.42. All right. Equals K, the concentration of NO2, which is 0.10, to the M, times the concentration of O3, which is 0.33, to the N. Now for 2, I want to do the same thing. Here the rate is 2.84 equals K. The NO2 is constant, 0.10 to the M. And this time, this is changed to 0.66 to the n. Divide, like that. Okay, once I've written both of them, what cancels out? K to the m, or k.1 to the m this time, cancels out. And what I get is 1.42 divided by 2.84 equals 0.33 divided by 0.66, and I'm going to write it a little bit differently this time, all to the n, which is the same as this. We just wrote it all to the n. This is 0.5 equals 0.5 to the n. And here we can see that n has to equal 1 because these are the same number. So 0.5 to the 1 is 0.5. So now we know both of these. We can rewrite our rate law now. Rate equals k. I should have written rate. Rate equals k, concentration NO2 to the 1, concentration O3 to the 1. But we don't write the 1. So I'm not going to write it in either case. Now I need to find K. It doesn't matter which reaction you pick. I'm going to pick reaction 1 just because it's first, but it makes no difference. 1.42 equals K, the concentration of NO2, 0.10, the concentration of O3, 0.33, and I'm omitting units here just for clarity because I just don't have enough space on the paper to write all the units out, so I'm just going to omit them for clarity. And what I end up with is 1.42 equals K times 0.1 times 0.33, which is 0.033. Divide both sides by 0.33, and I find that K equals 43 m to the minus 1 s to the minus 1. Okay, so now if I look here, I find that rate equals 43 m to the minus 1 s to the minus 1, and O2, O3, which is choice letter B. So this is how you can complete this problem. This is a very challenging problem, which is a lot of work. Question 5 says, for a reaction that follows the general rate law, rate equals K, concentration A, concentration B squared, what will happen to the rate of the reaction if the concentration of B is increased by a factor of 3? Well, we know that this reaction is second order with respect to B because it's B squared. So we take 3, because we're going to triple the concentration, and we square it. 3 squared is 9. So the rate of the reaction will increase by a factor of 9 because the reaction is second order with respect to B. If we tripled the concentration of A, the reaction would get 3 times faster. But if we triple the concentration of B, the reaction will get 9 times faster, again, because it's second order with respect to B. Question 6 says, how many half-lives are required for the concentration of reactant to decrease to 25% of its original value? Well, if we look at this, for every half-life, we're going to get half as much. So you may instantly realize that this is 2 half-lives, right? Because the first time we have 50% left, and then we go another one, and then half of the 50%, which is 25%. But how could you solve this if you didn't know? Well, it would be that 0.25 equals half, because it's a half-life, to some power. I'm going to call it n. Okay, so if this was a number where you didn't actually know that it's 2 half-lives just because half of half is 25%, this is how you could do it. So however much is left equals the half-life to the number of half-lives, n. How do you solve this? Well, log of 0.25 equals log of 0.5 to the n. So I take the log of both sides. Mathematically, because it's a logarithm now, this exponent goes outside. So I get log of 0.25 equals n log 0.5. Divide by log 0.5, divide by log 0.5, and you can either, again, realize this is 2 because this is half as much as this one, or you could actually plug this into your calculator and you find that n equals 2. So it takes 2 half-lives in order to get 25% of the original value. Again, for 25%, you could probably just do this in your head. But if it was like 1.25%, it would probably be easier to use this mathematical formula. All right, question 8 says, what data should be plotted to show that the experimental concentration of data fits a second order reaction? Well, in order to do this, we need to look at the integrated rate laws. And for a zero order, and I'm just going to write them all here. You really only need to know the second order one to answer this question, but I'm going to write them all here. It's the concentration of A after some time equals negative KT plus concentration A, 0 or initially. Okay, this is for an integrated zero order rate law. So if we look at this in terms of the equation of the line, y equals mx plus b. So the concentration of the reactant, A in this case, okay, would be the y value, and t would be the x value. So that's what we would want to graph if we wanted to see if it's a zero order reaction. For a first order, the integrated rate law is ln of the concentration of A at some time equals negative KT plus ln concentration A initially. Again, y equals mx plus b, the equation of a line. The y value would be the ln of the concentration of A, of the reactant, and the x value would again be time. And you're actually going to do this in the lab. For second order, it would be, the integrated rate law would be 1 over concentration of A at some time equals KT plus 1 over concentration of A, 0. So this is the second order integrated rate law. Again, y equals mx plus b. The y value should be 1 over the concentration of A, and the x value should be time. So if we look at choice letter E here, it says 1 over reactant, 1 over A, for your x versus time for your y. So this is y versus x, and this is basically how you're going to do this. You do need to know these integrated rate laws in order to solve for the concentration after some time, right? The rate law is good for some things, but if you want to know how much of A is left after a certain amount of time, the integrated rate law is very useful. Or conversely, if you want to know how much, if you have this much A left, how much time has gone by, the integrated rate laws are great. I don't know if they're given to you or not, so please check with your instructor on that, but these are something that you can commonly need to know. That's why I wanted to put all of them here for you. Question number 9 says, the rate constant for a second order reaction is 0.54 molar to the minus 1 second to the minus 1. What is the half-life of this reaction if the initial concentration is 0.33 molar? Well, this is given as a second order reaction. I want to go over the 3 half-lives because again I don't know if they're given to you, if you need to memorize them, but this is a second order reaction. I realized I read the question and it might not have been on the screen. So the rate constant for a second order reaction is 0.54. What is the half-life of this reaction if the initial concentration is 0.33? Sorry about that. So for zero order, the half-life, T1 half, is equal to concentration of A initially over 2K. And this is just basically a rearrangement of the integrated rate law. For a first order reaction, the T1 half is equal to 0.693 over K. And for second order, with the only one we really need for this problem, is the T1 half, the T1 half is equal to 1 over K times the concentration of A initially. Okay, where A is the reactant. So you'll notice here that for zero order and for second order, the concentration of A is in the half-life equation. Said another way, the half-lives are not constant. For first order, where half-life is constant, and this is important, okay, you'll notice the concentration of A0 is not here. So whether it's the first half or the second half or the third half, the rate of decomposition of half is a constant. That is not true for zero order and second order. Anyway, we can now that you have these, in case you need them, we can now solve for this one. So T1 half equals 1 over K, which is given, 0.54 molar to the minus 1, second to the minus 1, times the concentration of this initially, which is 0.33 molar. And when you do that math, you find that the half-life at this point is 5.6 seconds. But the half-life will change when there's a different initial concentration of the reactant in this case. So for this one, the answer is choice letter E. Question 9 says, the combustion of ethylene proceeds by the reaction. And then it gives the reaction. When the rate of disappearance of O2 is 0.28 molar second to the minus 1, what is the rate of appearance of CO2 in the same reaction? So in this case, what we need to do is we need to look at the stoichiometric relationship essentially between oxygen and CO2. So if we're losing the oxygen at a rate of 0.28, so what I would like to do is write the rate for the two, for the reactant and the product. So with respect to oxygen, the rate equals negative 1 over 3 concentration of O2 over time. And, sorry, these should be delta concentration in O2 over delta T. And for the rate of appearance of CO2, the rate equals positive 1 over 2, because there's a 2 here, delta concentration of CO2 over delta T. So this is from question 1 where we cover the rate with respect to products and reactants. So O2 is disappearing at this rate and CO2 is appearing at this rate. But these two rates are equal. Said another way, negative 1 over 3 concentration of delta concentration of O2 over delta T is equal to 1/2 delta concentration of CO2 over delta T. So these two things are equal because the rate of one disappearing and the rate of one appearing are the same. Now note that we're given the rate of disappearance. We're given this whole thing. We're not looking for these variables individually. And we're looking for this whole thing. We're not looking for these variables individually. Also notice that this is the rate of disappearance. So this is negative. So it's negative 1/3 times negative 0.28 molar second to the minus 1 equals 1/2 times delta concentration CO2 over delta T. When we multiply these two things together, we get 1/2, I'm just going to switch sides, delta concentration of CO2 over delta T is equal to negative 1/3 times negative 0.28 is 0.093333, lots of 3's. Now we divide by 1/2, and we get the rate, delta concentration of CO2 over delta T is equal to 0.19. This is the rate. We don't need to solve for these individually, so the answer is choice letter C. Notice that this is the same thing as just changing the stoichiometry because there are 2 CO2 for every 3 O2, so we essentially multiply by 2 and then divide by 3, but this is why that is the case. So I went through it kind of the long way, if you will, but that is why it's the case. Before I start this question, I just want to remind you that in question 7, I go over the integrated rate laws in case you don't have those memorized or on your sheet. I'm not sure if you get them or not, so please be sure with your instructor on that one. It says the first order decomposition of N2O5 at 328 K has a rate constant of, and it's given. If the initial concentration of N2O5 is 2.88 molar, what is the concentration after 12.5 minutes? Well, a couple things here. First of all, the rate is per second, so we can't use 12.5 minutes. We have to multiply that by 60, and we find that it's 750 seconds. That's important. So the first order rate law is the ln of the concentration of N2O5 at time is equal to negative K T plus the initial concentration of N2O5. And in question 7, I gave it as A, but it's the same thing. This is the reactant A that we're talking about. So now let's plug in what we know. Well, what we don't know is this. So that's our X, or our variable. So the ln of the concentration of N2O5 after some time is equal to negative K, which is here, negative 1.70 times 10 to the minus 3 seconds to the minus 1, times the time. Remember, I had to change that to seconds because this is per second. So 750 seconds plus the ln of the initial concentration of the N2O5, which is given, which is 2.88. And I'm going to omit units here for clarity. Okay, so when you do that, you find that the ln of the concentration of N2O5 at some time is equal to this times this, which is negative 1.275, and the ln of 2.88 is plus 1.058. Now we add those together and we get that the ln, move this over a little bit, of the N2O5 at some time is equal to 0.2172. Now in your calculator, you have to do the opposite of the ln, which is e to the x, so e to this power. In this case, e to the ln is the concentration of N2O5 at some time. The ln just disappears. E to this, you have to do in the calculator, and you get 0.805 molar. So after the 12.5 minutes, the new concentration is 0.805 molar. Choice letter A. Number 11 says, the second order decomposition of NO2 has a rate constant of 0.225, and it says how much NO2 decomposes in 4 seconds if the initial concentration of NO2 in 1 liter is 1.33 molar. This 1 liter ends up being important at the end because since it's 1 liter, whether it's moles or molar, it's the same thing, right? Because there's the same number of moles as there is molarity if the volume is 1 liter, right? If a solution is 1 molar, that means there's 1 mole per liter. If it's 2 molar, there's 2 moles in a liter. So that's not super important, but it does play a role at the end. All right, so in question 7, I go over the integrated rate laws, but here we want to use the second order integrated rate law because we want to find out how much is left after some time, and then we can figure out how much was gone. So that is 1 over the concentration of NO2 at some time equals KT plus 1 over concentration of NO2 initially. So this is the integrated second order rate law. Again, in question 7, I go over all the integrated rate laws. I'm not sure if you have to memorize those or not. So the 1 over the concentration of NO2 at some time equals K. K is given, 0.255 molar to the minus 1, seconds to the minus 1, times the time that we're given is 4 seconds. It's given here. Plus 1 over the initial concentration of NO2, which is 1.33 molar. When we do that math, we find that 1 over the concentration of NO2 at some time equals, we take this times this and then just add it to 1 over this, is 1.77 molar to the minus 1. When we do this, what we do is we take the reciprocal. So we just take the reciprocal of this. We take 1 divided by 1.77, and we find that the concentration of NO2 after some time is equal to 0.56 molar. Now this is important because 0.56 molar essentially shows up as an answer. Remember, because it's 1 liter, whether this is molar or moles, it's the same unit. So that's important. However, why isn't this the answer? Because it asks us for how much decomposes. So we started off at 1.33 molar, and when we finished, we had 0.56 molar, which means that what we lost is actually 0.77 molar. However, because it's 1 liter of solution, that also means that we lost 0.77 moles in 1 liter. So this is actually the answer because it asks us for how much decomposes, not how much is left. This is the concentration after some time. It doesn't tell you how much you lost, it tells you how much is left. But how much was lost is 0.77 moles. Not a particularly easy question, and I strongly recommend you practice this. If you look at the previous question, it goes over a first order, and this goes over a second order. These are similar questions. Question 12 says, for a reaction, what generally happens if the temperature is increased? Well, two things generally happen if the temperature is increased. One, there are more collisions because the molecules are moving more quickly. And two, there are more effective collisions because the collisions that occur in the right orientation will have enough energy to overcome the activation energy and go on to form product. So generally speaking, if the temperature increases, the K, the rate constant, increases and the rate of the reaction is faster. Note that temperature does not change the concentration. Temperature also does not change the reaction order. So if the rate speeds up when you increase the temperature, what changes is K, because rate equals K, concentration A, let's say it's first order, right? This isn't going to change when you change the temperature. So if the rate goes up, it's because K goes up. All right, a reaction is followed and found to have a rate constant of 3.36 times 10 to the 4 at 344 K, and a rate constant of 7.69 at 219 K. Determine the activation energy for this reaction. So this allows us to use what is called the 2-point Arrhenius equation. And this is something I think you just have to know. Maybe it'll be given to you that I don't know. So the ln of K2 over K1 equals EA over R. This is the 8.314 R, so the one in joules, and times 1 over T1 minus 1 over T2, where your temperatures need to be in Kelvin. So now we just plug into this because we're given most of this stuff. In fact, we're given everything except EA. Note that we aren't given R, but that's 8.314 joules per mole K. So plugging in ln, we need to decide which one we want to call 2. So I'm going to call this one 2 and this one 1. It doesn't actually matter as long as we are consistent. So let's just make sure we use this one with this one and this one with this one. So I'm going to call this 2 just because it's given second. So ln of the second one is 7.69 m minus 1 s minus 1 over the first one, 3.36 times 10 to the 4 molar minus 1 s minus 1 equals EA, that's my variable, that's what I'm looking for. R is 8.314 joules per mole K, I'm not going to write that out, times the temperatures in Kelvin. 1 over T1, which is the 344 K, whoops, I don't need that, minus 1 over T2, which is the 219 K. Now, it's a math problem. So, the first thing that we're going to do is divide these two numbers and take the ln. And what we find is, I'm going to kind of go over here, negative 8.382, which is these two numbers divided and then use the ln using a calculator, equals EA over R, which is 8.314. And then when we subtract these two numbers, we get negative 1.659 times 10 to the minus 3, and that's technically k to the minus 1, but I'm not going to write all the units out here. Okay, now we need to finish solving this. So first thing I want to do is take this and divide it into this. And then essentially what I'm going to get is negative 8.382 equals this one divided by this one, which is negative 1.996 times 10 to the minus 4 EA. Now divide by both sides by negative 1.996 times 10 to the minus 4. It'll cancel out over here. Divide by negative 1.996 times 10 to the minus 4 over here. And I get that the activation energy of this reaction is equal to 42,000 joules, or 42 kilojoules, and that is per mole. So it's 42 kilojoules per mole, which is choice letter E. So once you know the equation and plug it in, just make sure that you can do the math on your calculator and that you're getting the same answer. Like anything, you practice this a couple times and it becomes fairly straightforward. It says, given the following proposed mechanism, predict the rate law for the overall reaction. And if you look here, we're given the mechanism, which these are molecular reactions, so we can use the stoichiometric coefficients in these reactions in order to determine the rate law. Note that we have the slow step and the fast step. The rate of the reaction is based on the slow step. So here, when the first step is slow, and we have actual reactants in that step, the rate is equal to K times the concentration of NO2 to the 1, I'm not going to write it, concentration of Cl2 to the 1. Again, we can use stoichiometric coefficients because in the mechanism, these are molecular reactions. So we want to use it for the slow step. Fortunately, since the first step is the slow step and it's containing reactants, we can simply write it this way. This is harder when the second step is the slow step because sometimes it doesn't contain reactants, and in which case you have to do a bunch of rearrangement in order to figure that out. I don't have an example of that here. I'm not sure if it's going to be on your test or not. I don't usually put it on the test that I write, but that could be there or not, so you might want to check it out, the difference when the second step is slow, and there's a good examples in your textbook for that. But for this one, since the first step is slow and it contains reactants, it's just NO2 to the 1 and Cl2 to the 1 because we can use the stoichiometric coefficients due to the fact it's a molecular reaction. That gives us choice letter D. I hope you found this video helpful, and good luck on your test.